In this second video on random walks, we'll talk about properties of random walk. Okay, so we go again and talk about properties of random walk. This lesson covers expectation, variance. We already did some of that in the last video. And then now we talk about the idea of hitting probability. Here we focus on the simple symmetric random walk and extensions. So simple symmetric random walks is simply that case where there's equal probability of a of of reaching +1 and -1, 0.5 each. So here, definition of a random walk is defined as Sn, which is equal to x1 plus x2 plus all of that up to xn, where xi are independent and identically distributed random variables. And for a simple symmetric random walk, we have xi to be +1 with probability half, and xi is -1 with probability half. So there's equal chance of reaching +1 and -1. That's simple. In essence, it means that there's equal probability of going right and going left. So we talk about expectation of random walk, which we already dealt with in the last video. So using linearity of expectation, we know that expectation of Sn would have to be expectation of xi plus x1 plus x2 plus all of that up to xn. In essence, we have summation from I equals 1 to n of all the expectations of I. And if each xi has mean mu, then we say that the expectation of Sn is simply n multiplied by mu. So the expectation for a simple symmetric random walk will simply be +1 times half plus minus half times 1, which gives us 0. Therefore, the expectation of Sn for a simple symmetric random walk is equal to 0. We saw that in the last video too. So this means the walk has no drift. So a simple symmetric random walk has no drift because the expected value of Sn is 0. So expectation for biased random walk. So when we have a biased random walk, that means a random walk that, it's not evenly distributed. So there's a higher chance of going right or going left than so it is biased because maybe the chance of going right is higher than the chance of going left. That's biased. If the chance of going left is higher than the chance of going right, it's also biased. But it is unbiased when it is symmetric, where the probability of either going right or left is exactly the same. So if the probability of xi equals +1 is p, and the probability of xi equals -1 is 1 minus p, then we say that the expected value of xi is 2p minus 1. Okay? Then if you take n steps, then it means you have n into 2p minus 1, which we saw in the other video. So if p is greater than or equal to 0.5, we have an upward drift. Okay. And if p is less than 0.5, we have a downward drift like that. Okay. So then we have a simple simulation here for a simple random walk. So like right here. So in this case, the final position is -36. So if you look at it, it's a symmetric random walk because p is 0.5, and then we have p and 1 minus p. So if I run it again, of course, we are going to get something different. What is it saying? Uh, connect to runtime. Connect to runtime. What does that mean? Should I change runtime now? Okay, maybe that's not necessary. Can just cancel and run it again. Okay, it's responding. So I just want to show that the more it's run, the more it changes. So final position in this case is -36, for instance. But now that I've rerun it, final position is 34. So based on the whole, everything is random, right? So here 28, here to -24. It just keeps going on and on like that. Just keeps going like that. So yeah. Now, let's talk about the variance of random walk, which we also saw in the last video, but here we have a bit more focus trying to prove how we derive them. So since xi are independent, because we're talking about a simple symmetric random walk, so the variance of Sn will have to be summation from I equals 1 to n of variance of each xi because they are independent. So if each xi has variance sigma squared, then the variance of Sn will have to be n sigma squared. So now, when we talk about variance for a simple symmetric random walk, so we have variance of xi equals to expectation of xi squared minus expectation of xi all squared. Then we already know that So for expression of xi squared, that is equal to 1. And expression of xi, especially we already do expression of xi for a random walk, for a symmetric random walk is actually 0. So 0 squared is 0. So we get 1 for this. So in essence, we say that the variance of Sn is n. That's just n times 1 like that. So the standard deviation will then be square root of n. This shows diffusive behavior. So the variance shows diffusive behavior. So then we try to, okay, we have some kind of Python verification for variance now. So we define a function called simulate variance, taking 5,000 trials, and we do all of that. Then we now check when n is 10, that's 10 steps, 50 steps, 100 steps, 500 steps, and we check. So each time you run, something changes. This is 10 point something, 51 point something, 100 point something, 516 point something. We run again, 9, 49, 97, 507. You discover that the values are close to you know the numbers, right? So 9 is close to 10. The variance is close to the number of steps. And of course, we already know that the number of steps is directly proportional to the variance, or variance is directly proportional to the number of steps. So then we talk about the idea of heating probability, which is a new concept so far. So define the heating time. So TA is the infimum of all n greater than or equal to 0, such that Sn is equal to A. So so the infimum of the smallest value of every n greater than or equal to 0 as far as Sn is equal to A. So this is the first time the random walk reaches level A. So we study, so in a random walk, right, a particular point can be hit several times, but the first time it hits that point is called the hitting probability. I mean, the first time it hits is that first one, right? So this is the first time the random walk reaches level A. So we studied probability hit A, for instance, for hitting probability. So we start with recurrence property for a 1D simple symmetric random walk. So for a one-dimensional symmetric random walk, the probability of hitting A is equal to 1 for any integer A. So this means the walk is recurrent. It will eventually reach every point. So that is, if the probability of hitting any point A is equal to 1, it means it will hit every point in the long run. Then we talk about the gambler's ruin problem. So here we start at position I, then we have boundaries at 0 and n. So starting point and the end point, for instance, and then ui can be said to be the probability hitting n before hitting 0. That's the probability of getting to n before getting to 0. So that's what we define ui as, and from that we can then say that the solution, uh, simple symmetric random walk. So UI in that case is I, that's the position I, all over the final position. So that's for symmetric, but for a biased case, things are a bit more complicated. So for a biased case, see what you get. You have UI, that is the probability, right? Probability of hitting n before hitting 0. So it is 1 minus q over p raised power I all over 1 minus q over p raised power big N when p is not equal to q. But when p is equal to q, and they are 0.5, each is 0.5, then we revert to the symmetric random walk situation, which is 1 over I over n for the bias, like that, right? So we have an example. So if you start at I equals 3 and you have boundaries at 0 and n over 10, then u3, all right, will be, so that's the probability that you hit uh the end before you go back to get to 0. So that is 3 over 10. So, and that is 0.3. So the probability of reaching 10 before 0 is 0.3, like that. And of course, if you simulate it here, you get 0.2966, which is pretty close to which is approximately 0.3 to one decimal place, like that. So that's what we get. So if you keep simulating, you have values hovering around 0.3. This is 0.311. This is 0.2978. This is 0.2958. This is 0.2998. This is 0.3092, and so on and so forth. So you keep having values around 0.3. In summary, we have this that for for simple symmetric random walk, the expectation is always zero, the variance is n, the standard deviation is square root of n because standard deviation is square root of variance, right? Then for recurrence, it hits every point with probability 1. And for Gambler's ring, we have I over n like that. Then key insights, expectation describes drift, right? Variance describes spread. So expectation is drift, variance is spread. Hitting probability describes long-term behavior. So we have some practice problems again. So expectation, let Sn be x1 plus all of that up to xn, where xi is plus or minus 1 with equal probability. Compute E sub Sn. Of course, that's simply 0 because there's equal probability of reaching plus 1 and minus 1. Then suppose P, probability of xi equals 1 is 0.7, probability of xi equals minus 1 is 0.3. Find ES 100. Okay, find ES 100. I think we just have the formula for, so we know that the expectation of Sn as usual is n into 2p minus 1. That's the formula. So if you're looking for ES 100, where we are given n, that means n is 100, right? So we are looking for ES 100. That means n is 100 and p. So p in this case now is 0.7 here. So that is P is 0.7. And with this, we have everything we need. So now we have the expected value of S100 is equal to N. N is 100 into 2P minus 1. So that is 2 into 0.7 minus 1. So that is 100 into 1.4 minus 1. So that is 100 into 1.4 minus 1 is 0.4, and that is 40, right? Yeah, that's 40. So the expected value in that case is 40. Then, yeah, so expectation of xi is mu, and mu is minus 0.2. Compute S50. Compute S50. So the expected value of xi is minus 0.2. Okay, let me just go and see what that looks like. Mm, mu. I think we had something about mu already before. So um, I think that can help with this now. Okay, we have expected value of Sn is n mu. Okay, n mu for, yeah, we have n mu. Okay, so with n mu, we can just multiply by n, right? So this now, expected value of xi is mu, that's minus 0.2. So compute expected value of S50. That's simply 50 times mu. That's 50 times minus 0.5. That is simply 5 times 2, 10. That's minus 10, basically. Then show that expected value of Sn minus Sm is n minus m mu. So we know expected, okay, maybe I should just write that out. So n minus m mu. Expected value to show that the expected value of Sn minus Sm is equal to n minus m mu. Okay, what do? We have expected value of Sn minus Sm. Based on linearity, that's simply the same thing as expected value of Sn minus expected value of Sm. And expected value of Sn, we know that should be n, it should be n mu minus m mu. So that means mu is common. So we have n minus m mu. And that's what we are expected to prove like that. So random walk starts at S0 equals 5. Find expected value of Sn for SSRR. Expected value is 0, so don't stress at all. Once it is simple symmetric random walk, the expected value is always 0, no matter how many steps are taken. Yeah, so with that now, let's so try your hands on the rest. Variance, just use the formula. Of course, for simple symmetric random walk, the we want to compute the variance of Sn. The variance of Sn is simply n, basically. Then if the variance of xi is 4, find variance of S20. Again, I think this comes with the idea of n sigma squared. So that would be 20 times 4, 80 or something like that. We already had it derived. Okay, let me just be sure of that. I think it's n sigma squared. Sigma squared is variance. So we just multiply the variance by n and we're good to go. Where is that now? Ooh, expectation there. Variance, yeah. So it's n sigma squared. So just multiply the variance by the number of walks and we are good to go there. So this is 20 times 4, 80. So variance xi is 4. So this 4 is sigma squared. So just multiply by this. Complete the standard deviation of S100 for SSR. So the variance, standard deviation, that's just square root of 100, which is 10. And that's it. Then for variance Sn minus Sn, Sm, of course, we know that the variance of Sn is n sigma squared. Variance of Sm is m sigma squared. And we just get, we just factorize sigma out and we have all of that. Then probability 0.6 and variance xi and then S50. So basically, we just need to use the same thing. So that's variance S50 is n sigma. Okay, compute variance xi. So variance xi would have to be 0.6 n. Now that n is 50, so we have what am I saying here? Probability of xi is 0.5. So variance of xi. Yeah, I mean, just use the formula you get and you compute distribution and properties and all the rest. So try your hands on this as much as possible. So let me know how helpful this whole thing is for you. Of course, there's also the idea of hitting probability. So try your hands. Let's see how well you get the gist. Let me know how helpful this is. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, what are you waiting for? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. And that gives you special privileges like getting to see some videos before other people. Or you can also be the only one to see certain videos because you're a member of the channel. You can also hang out with me. You can ask for PDF copies of the notes I'm using. And of course, we can do so many things together based on just click on join. You find all of those things. Then ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Don't forget to try your hands on the practice problems and let me know what your answer might be in the comment section. Or if you have issues try solving any of the problems, you can also let me know so I might make another video to address your concerns. Until I come your way again, keep doing maths right. Bye.